good morning, and thank you again for that very kind introduction. So I have some slides, if we can call those up, please. Thank you. All right, so I thought I would talk a little bit about our journey through this very exciting time to be involved in space. We have new entrants, we have new missions, there is a new energy in our country behind going to the moon and going beyond to Mars and really seeing a renaissance in our interest in space. And so I thought I would share with you a little bit about our journey through that, as well as a bit of a focus on our progress on the Vulcan launch system. And I have some photos and things for you today that have not been released before, so some breaking news, if you will. But first, a little bit about who we are. Let's go ahead and run the video, please. All right, well, there's just nothing like seeing a 30-story building blasted into space on a fountain of fire. So I hope you enjoyed that video. I never go anywhere without showing some smoke and fire. Everyone at ULA comes to work every day to do three things. This is why I get up at 3:30, believe it or not, every morning to come into work, and it's what motivates every single one of our employees. The first is literally to save lives. We take this mission so very seriously, and as you gather maybe from the photographs that are on the slide, it is integral to the way that our country functions overseas and at home. If there is a soldier overseas who gets in harm's way and they need to pick up the radio and they need to call for help, we help make that possible, and we take that mission extraordinarily seriously. And as you see in the other graphic, our abilities to support the country in its efforts to get accurate weather predictions, especially recently with the GO satellites that have gone up that have near real-time tracking of things like hurricanes that can allow us to properly and accurately evacuate areas, position support, have literally saved thousands of lives. It is a mission that is very, very important to me personally and to everyone in our company. The second thing we come to work to do is exploration. We have been to every celestial body in this solar system of any interest, every planet and beyond that. If you're like me, you spent Monday watching InSight land on Mars, a historic mission, a very important mission that we helped by launching it back in May. It was so very exciting to see that, and it was our 18th trip to Mars, and we hope to do more in the future. After that, later in the summer, we launched the Parker Solar Probe, an amazing mission, a probe that is now the fastest human object in the universe, traveling at over 153,000 miles per hour, and after it completes its major Venusian flybys, it will be at over 430,000 miles per hour as it literally flies through the corona of the sun, gathering groundbreaking science. And to support missions like that is truly, truly inspiring. And of course, even in our commercial world, we help make this planet a smaller and more connected place. We provide commercial support. If you have ever looked at, say, Google Earth, chances are we put up the satellites that took the pictures you're looking at. But even more than that, because these services do not only go to developed countries, but they go to other places where in prior times, very recent times, those regions have had very limited access to data. And in a few cases, have perhaps even lived under the boot of tyranny. And as you know, information is power, and freedom begins first in the mind. So these are just as important as missions as well. And now, finally, very soon, we will help return humans to space from American soil, and it is about damn time. And so we could not be more proud to work with our partner Boeing, our customer Boeing, to take that fabulous crew of truly inspiring astronauts and human beings back to space very, very soon. Now, we have a mission success culture at ULA. That manifests in 1,000 different ways on any given day at work, but ultimately what it means is that nothing trumps mission success for us. But when we talk about putting people on top of a million-pound rocket, it takes it to a whole nother level. And I would just tell you that we know our astronauts, they've been to our facilities, they come to our factory every so often to kick the tires on their rockets. They are wonderful people, and it is a whole nother thing for us because these are not just a payload, these are people. These are sons and daughters, mothers and fathers, husbands and wives, and we take this responsibility incredibly seriously. And by the way, are very, very happy to work with Boeing, who has a safety culture that is second to none and completely compatible with the way we look at this mission as well. And there they are in front of the Starliner, and the photo below that is their Centaur upper stage in its dual engine configuration. Configured that way specifically for safety. It allows us to fly a trajectory that supports scenarios for abort, God forbid that should ever be necessary. So very, very exciting mission, and everyone at ULA really, certainly me personally, cannot be more thrilled to be a part of this. It was mentioned that we've flown 131 times. If you'll forgive me, I'll mention it again. We have flown 131 times. We have never failed to take our payload to space. This is a chart we use internally to remind us of the nature of that work. One mission, one box on that chart is more important than all the others. And it's actually the one down at the bottom that's blank, because it is 131 successful missions, one mission at a time. That's what it takes to pull that off. All right, so I'm going to talk a little bit now in the next few slides about Vulcan and about our transformation. So I came to ULA about 4.5 years ago, and my job was to carry our company from the company our nation needed 10 years ago, a decade ago, to the company that it needs today and into the future. And that meant reorganizing our company, restructuring our supply chain, drastically reducing our costs, significantly shortening the time it takes to go to space, collapsing our build times by about 50%, collapsing the time it takes to integrate a spacecraft and bring off a launch by over 2/3, all the while maintaining that perfect reliability we talked about, also maintaining the highest schedule certainty in the industry, and as we also believe, eye-watering accuracy that is really second to none across the world when we actually go to space. All of that while still supporting what is today our unique ability to fly every single payload to every single orbit in even new and even more exquisite and complex and higher energy orbits that our nation will need as we go into the future. And so I've talked about 131. There's another number that I'm personally very proud of as well. That number is 51. That is the number of perfect missions that we have conducted while transiting through this tremendous set of changes, maintaining our support to our country and our customers, literally while sort of driving a race car down the track and changing its tires at the same time. And so now we are at the final, most important part of that, which is the introduction of a new launch system, the Vulcan vehicle. This is just a sampling of the typical orbits that Vulcan will fly to. We call it the Big 9. There's Big 8 today, but as we go forward, there's even more need and larger payloads going to these. It is a certain kind of relatively straightforward mission when we fly to LEO, for example, or even to geosynchronous transfer orbit. But as we go to the higher energy orbits that you would see on this slide, this requires very unique capabilities, particularly in an upper stage. These are exquisite orbits that are very complex to achieve and take many, many hours of flight time to do them. This picture that I'm showing you is not to scale. Those last two orbits out there, geosynchronous or directly injected specifically to geosynchronous and geosynchronous transfer, are not to scale. If they were, then the loops you see on my left would extend all the way past the loops on the right. That is literally how much space has. Vulcan will serve all of those missions and greatly simplify the product offering that we bring to the marketplace. So let me start with that idea first. Now, in order to be our country's provider of any payload to any orbit, we've maintained a fleet of launch vehicles, several different families and many different configurations, literally 41 different rockets to do that mission. We have been simplifying that over time. We're now underneath 20, as you can see, 18. And as we go to Vulcan, that will collapse to something in the neighborhood of 4. That means that it is much more efficient to build these vehicles, it is faster to launch them, and it is much more affordable to accomplish that mission. Now, Vulcan represents a couple of things. First, sort of the ultimate evolution of the best parts of the Delta Launch System family and Atlas, but also together with new technology. And to give you a feel for that, I'll just kind of walk down a couple of the elements on this slide. So we will be bringing our 5.4 meter diameter composite fairing across onto Vulcan, but this will be manufactured with advanced techniques out of autoclave and made in Decatur, Alabama, where it was formerly made in Europe. So we have brought industry and jobs to America from overseas, and that will first fly on Atlas in just year after next, and then transition onto Vulcan when Vulcan is ready. We have today the highest energy upper stage in the world, the Centaur 3. It is so important to have high performance for those complex and exquisite orbits in your upper stage. When we talk about a booster, just to give you a feel for this, about 7 pounds of mass on that booster that is not propellant will cost you about a pound of payload. But when we get to the upper stage, every kilogram of material in that stage that is not propellant costs you a kilogram of mass in your payload. And so performance is critical, and that's why we fly the Centaur. It is constructed from thin-walled steel tanks. It's like a soda can. Without propellant or pressure, it cannot even support its own weight and would collapse onto its own shape. It is that sophisticated. And as we go forward into Vulcan, we're going to bring that same technology forward, but we're going to scale it up, and we're going to put twice the amount of energy in that stage. And at the same time, we're going to make it so much more simple and easier and faster and less expensive to fabricate. It will start first with the existing RL-10 engines from Aerojet Rocketdyne, some of the most high-performance upper stage engines flying, but those will also later be upgraded to even higher performance, a high degree of additive manufacturing, and increased thrust. We'll also take the common avionics suite that we have just finished developing and is now flying on Delta and Atlas. We'll bring that forward onto Vulcan, thus lowering the risk of having developed new avionics technology, but of course with new software. We'll have new SRMs on Vulcan. We'll have what we call the GEM 63XL for extra long. These will be the longest single-segment solid rocket motors ever produced. A 5-foot shorter version of that, called the GEM 63, will begin flying on Atlas next year. So we'll be burning down the risk as we bring these elements forward before Vulcan actually does its flight. And of course, on the first stage, we will also now bring the advanced technology of the oxygen-rich stage combustion engine cycle, very high performance engine cycle, through the BE-4 onto that first stage, retiring, of course, the venerable RD-180 that we fly today on Atlas. So a combination of evolution and also new and advanced technology and manufacturing techniques where that makes a difference. And in terms of the performance of this vehicle, I'll just direct your attention kind of to the center when we compare it to the Delta IV. The Vulcan in a single stick configuration will have at least 25% more lift capability than the 3-core Delta IV Heavy, and do that at about a quarter of the cost. So a tremendous jump forward in heavy lift. As we compare it to Atlas, we see also big differences in the performance. The blue, of course, bars on that, vertical axis being mass to orbit. For different orbits, blue being Atlas, red is Vulcan. You can see the giant difference, especially as we go to the higher energy orbits, the ones that are most critical to national security. What may be a little bit hard to read on the slide also is when you look at those payload fairing notes up there, you'll see that we have greater than a 55% increase in payload volume on the Vulcan over Atlas. So tremendous flexibility and the ability to take multiple payloads to space at the same time. We are also doing for the propulsion industrial base in America, in a way, what we are seeing happen in the launch industrial base. Where we are seeing more players and a broader base, which is good for our country. We will be retiring the Aerojet RS-68s off of Delta, but we're maintaining and significantly improving the Aerojet Rocketdyne RL-10, while also adding a domestic provider for the BE-4 from Blue Origin. So a broader industrial base that our country will benefit from. Now, it's not just about the rocket. It's also about how it's built and how it's launched. So I'm going to talk a little bit about our factory in Decatur, as well as our launch sites. Now, we have a lot of flexibility out in Decatur. It is the Western world's largest rocket factory at over 1.6 million square feet of production space. And then, of course, we launch from both coasts, as you well know, and we will be using the Atlas pads for Vulcan, even as Atlas continues to fly. And then for fun, I threw in this little picture down here in the corner that you see with that giant photo on the side of our building. That is the high bay at our Decatur factory. One of the things that I'm always struck in our business is the scale of what we do and the scale of what we build. And even when we look at the rockets and walk up and touch them on the pads out of Cape Canaveral or Vandenberg, because there's nothing around them, it's still hard to grasp just how gigantic those are. So I actually asked the team to take a 1-to-1 scale photo and put it on the side of our Decatur factory. And that's what you're looking at. And if you have sharp eyes in that photo, you can see sort of a little arm reach up in a little basket, and that little dot inside that's a human being in a cherry picker helping to install that photo right now as we speak. All right, significant capital improvements in this factory. So while we're updating the design and the technology in the rocket, we're doing the same for how it's made. So you're looking at a giant universal weld system there in the top of that photograph that will be doing ring and dome welding on this much larger rocket. Below that is a circumferential friction stir welder, which gives us much stronger welds because of the nature of that technology, which also allows us to have thinner walls in our tanks and higher performance in our rocket. There will also be a significant amount of additive manufacturing in various components throughout the rocket, further lowering the cost and allowing us to do designs that would otherwise not be manufacturable. On the lower left hand of this slide, you're seeing a photograph of the main thrust structure elements. These are very high performance structural pieces at the base of the booster that are going to transmit that 1.3 million pounds of thrust into the body of the rocket at a minimum amount of weight. And of course, we always like to include, when we can, a person so you get a feel for that. And if you look at that top photo with a group of people, far to the right is the person that represents our SBR, our standard Brian reference. Brian is one of our engineers down at Decatur. We like him to be in all of our photos. That doesn't happen to be Brian, but we do have a substitute who has been chosen to be the same height as Brian. Over on the right, you can see the C-gun welder for our Centaur 5. This is a Centaur, as I said, same type of technology as Centaur 3, but of course much larger, twice the amount of energy. The Centaur 3, as high performance as it is difficult to manufacture. It has over 180,000 welds in that one stage. All of those set up by hand. And so we are moving that to an automated process. We've knocked the number of welds down by an order of magnitude and then automated that so that we have much higher consistency and therefore higher quality and much shorter build spans. In addition to that, we're working on the other parts. So what you're looking at in the top left hand of that cluster of photos is the structural test case for the new GEM 63 solid rocket motors. And right next to it, that cloud of smoke is the exhaust plume from a static firing that we just conducted a couple of months ago out in Utah. Beneath that, on the left, you see our first structural test asset of the 5-meter payload fairing, composite, manufactured out of autoclave, which is a significant reduction in the time required to manufacture, the touch labor to do that, and of course, we also expect much higher quality. That is in our Decatur factory. Again, jobs moved from Europe back here into the US, made in the USA. And in the bottom right, a full-scale static firing of the BE4 oxygen-rich stage combustion engine, high-performance engine, also burning a novel fuel, methane, made from liquefied natural gas, cheap and plentiful domestically here in the US, but this also represents a scaling up of the largest prior methane engine by about a factor of 1,000, believe it or not. The pads are also being modified, and so this is something that, to our knowledge, has never been done before, where we are going to fly 2 rockets off the same pad, very different sizes. And so that means we need flexible launch sites with platforms that can go up and down and accommodate different diameters. You can see that some of that annotated in that lower picture. The one in the upper left might be a little bit hard to figure out what's going on there. So you're standing inside the vertical integration facility, you're looking down onto a platform about 3 to 4 stories beneath you. The white cylinders on the right side of that photograph are solid rocket motors. And the reason the deck appears to be made out of planks is because that is a platform that is made from fingers that can literally come in and conform to any shape of booster and SRM combination that is present in that facility. On the right, you see a brand new mobile launch platform being fabricated, because Vulcan will have a dedicated MLP but share our vertical integration facility. And so we'll have a very flexible platform. We've been building that all this year. So we fly an Atlas, we run out, we make modifications to the facility, we make sure it's all okay to fly another Atlas, we run away, then we fly another Atlas, and so on until we're done. And so that process was pioneered for the Crew Access Tower for our human spaceflight missions. And again, as far as we know, this will be the only multi-use launch platform for different rockets that has ever been done. Okay, and so all of that means that the factory has been retooled. We are now fabricating our qualification and test hardware, and very soon we'll be fabricating the actual first flight units for that Vulcan launch. We have high confidence because of our design approach and because of how mature we are now in that process. So pretty exciting time for us. Now I'm going to shift gears a little bit, and I'm going to talk about the potential and the vision we have for a new epoch, really, in human history, as our country has picked up this mantle of going back to the moon to stay and pushing onto Mars and really developing this cislunar environment that exists between here and the moon and on the surface of the moon. All of these new transportation systems that we are pioneering, and Boeing and Lockheed and all the other companies are involved with in the direction of the U.S. Space Council, are heading towards a set of infrastructure that will potentially make what I'm going to describe to you possible, and that is a post-scarcity human future. A completely different environment than we will live in than we have ever lived in before, because there are tremendous natural resources in that region of space, so very close here to Earth, to our home. Now, we have spent all of human history in an environment where we struggle for natural resources, and in today, natural resources that are ever diminishing often, unfortunately, and sadly, in struggle and turmoil and conflict, when yet right there, less than a week's journey from where you and I stand in this very room, resides such abundance that it defies human imagination. NASA's exploration activities have allowed us to understand now that there are about 17,000 near-Earth objects, asteroids, in that region of space. And they contain more than 1,000 years of Earth's total annual production of industrial metals. And in terms of precious metals, gold, platinum, silver, more than has ever been developed, mined, and discovered in the history of humanity. Right there. And we are living in an age where you and I in our lifetimes are going to see that developed and exploited for the benefit of humanity, and it will completely change everything here on Earth. This is a very exciting time to be involved in space. And so we have brought together our Cislunar 1000, our Cislunar Marketplace community of startup and entrepreneurial companies that are interested in being a part of that want to prospect and mine and do specialty manufacturing in space and leverage the tremendous research in the International Space Station and other platforms to help make this vision that I've described to you come to pass. We get them together several times a year. We have conferences, we do studies. We've just published a report that I encourage you to go look at. And so with that, I believe that I'm out of slides and I'm done talking, and I just want to say again how much I appreciate that you have taken the time to be here with me this morning, and how very excited I am to be a part of this bold future in space in a new epoch in human history. Thank you all.